So when we look at this, we're going to start with some basic soil fertility. So I'm trying to set us up for the rest of the day because you have some amazing speakers coming up, and I just want to remind us of things that we already know. So when we think about basic soil fertility, we can argue whether there's 16, 17, or 18 essential nutrients, but I'm going to go with 18, right? So that's what I want today. I'll go with the most. So there are 18 essential nutrients for plant growth. As you can see from the slide, what defines an essential nutrient? Well, it's something the plant needs to carry out its life cycle. It can't be replaced by another nutrient. It must be involved in metabolism. But what are these 18 essential nutrients? And you're looking at this thinking, Jamie, what is that? I can always remember them. It's C. Hopkins Cafe, managed by my cousin. I spent 10 years in Missouri, not quite Georgia, but we got cousin Mo Nickel, right? So C. Hopkins Cafe, managed by my cousin Mo Nickel. All right, so those are the 18 essential nutrients. Carbon, hydrogen, and oxygen are in the beginning, right? Those are the ones that we get from water and air, and I kind of just push those off, right? They're not coming from my soil. I have a background in soil pedology, okay? So you're gonna see I have a really global way of thinking. I'm all about touching, feeling, tasting, smelling soil. You're gonna hear from scientists today that are gonna talk about analyzing it, but in all reality, I'm happiest standing in a soil pit, sitting down there all by myself, just staring at that beautiful body of soil, right? So you're gonna see that's kind of the perspective I take when I give these presentations. So we have carbon, hydrogen, oxygen in the beginning, not coming from my soil. I then have my macronutrients, the ones needed in the greatest amounts. They're not more important, they're just needed in greater amounts. Notice they're in the beginning. NPK, calcium, magnesium, and sulfur, and then the rest of the micros. So when we think about this, I think this is absolutely amazing. When we look at this beautiful soil body that we have, I was asked these questions. How many of you have ever fertilized for cobalt? A few of you. Nickel? Copper? Most of us don't even think about some of these things. Those of you who are a little more progressive in micronutrients, you're saying yes, but most of us don't ever think about them. They just naturally come from the soil body, right? And so managing these soils and the quality and the health of them is very important. That's where our fertility comes from. So just a quick slide, macro versus micro. Again, one's not more important than the other. It's just that ones are needed in greater amounts, tens to hundreds of times greater amounts than others. And we're looking at those plant available forms. When we're talking about, we're going to talk about soil organic matter a lot here. When we look at soil organic matter, remember that plants primarily take up the inorganic forms of these nutrients. I have to break down that organic matter. I have to break down that organic source of fertility. And when I say I'm speaking for the microbes, right? Me and the microbes. Break that down into those forms that the plant can take up. So when we look at additions and losses, again, just to summarize, I know you all know this, but I'm putting us in the mindset so that we can start talking about soil health and start talking about managing our soils as a body. When we look at those additions, we get nutrients from weathering, right? Those minerals, rocks and minerals in our soil, as they break down, they release nutrients. We have mineralization. Okay, that's just the conversion of those organic forms of nutrients into the inorganic forms that the plants primarily take up. We have N fixation. You're going to hear a lot about using legume cover crops to incorporate atmospheric nitrogen into a form into the soil that the plant can use. Atmospheric deposition, right? Stuff falls out of the sky. Sulfur used to fall out of the sky in greater amounts than it does now, but we cleaned up the air and we have less fertilization via that method now. And of course, fertilization itself and those losses. But I'm going to talk mostly about soil fertility, but when we look at those losses, I do want to point out one thing. As a soil scientist, I would be completely amiss if I left out soil pH. Right? We're going to talk about fertility, but pH is probably one of the biggest driving factors of nutrient availability within our soil. And most of you know this. This is a bioavailability graph of pH and many of our nutrients. Right? There's a reason why universities say that we need to, for most crops and certain crops, raise that pH up to 6.5 to 7. Why? You'll notice where are those bars, the bioavailability, the amount of those nutrients most available, it's in that 6.5 to 7 range, right? It's that delicate balance between keeping those macronutrients, the NPK, calcium, magnesium, sulfur, those tend to be more available at higher pHs. So balancing that out with the micronutrients, which tend to be more available at the lower pHs, right? There's always exceptions to the rule, but that's in general, right? So soil pH, when we go back to those losses, When we talk about transformation, we have to remember that just because that nutrient is in the soil doesn't mean that a plant can take it up. It may simply be in a form that it can't use, right? And one of those forms may be these chemical transformations that come about if our pH isn't in a range that we want. All right, you're already bored, all right? Sorry, all right? Sorry. So think back to State Street, bring this gentleman, it looks like Max. Max, he's smiling now, all right? Yes, I have got new glasses on Wednesday. I can read your name from here. This is terrible, all right? So think back, be excited again, all right? Get some caffeine, there's lots of coffee back there. Lo and behold, no, I haven't had caffeine today. I don't drink caffeine, it's a shock, I know. Mull that over in your head. All right, so how do plants actually get nutrients? It's through acquisition, and this is what's gonna be important. When I start to talk about soil health, and when I get really animated about soil structure, and I get really animated about cover crops, this is what's going on in my brain. You probably didn't think about that, but this is what I see in my head when I'm looking at that beautiful crumbly cookie crumb structured soil, is this little plant root, right? And how that plant root gets nutrients. When we think about the three mechanisms in which a plant can take up nutrients, right? There's three basic of our understanding. We have mass flow. Basically, nutrients come to that plant root with water. So as that plant takes up water and water's being sucked into that plant, nutrients are just coming along with it. Those are our mobile nutrients, things such as nitrate. When we look at the other nutrients, some of them, the plant root has to come in contact with it. Root interception, right? Think about that. When we think about soil health and getting a big healthy root system, right? And I see all those little fibrous roots out there, I get really excited because all I see is root interception, right? Those roots coming in contact with that nutrient. And we also have diffusion. So from high concentration to low concentration. Why this is important to me, and when you think about it, diffusion, those nutrients don't move very far. In fact, they maybe move a centimeter total. That's a little under a half an inch. Ooh, now I can't see you, so now I can't read Max's name. All right, good job. All right, Erin's laughing. All right, she's protecting you from me, is what's happening. All right, liven up. All right, so that diffusion, those nutrients are only moving a very small amount. What that means, again, is that root system has to be there. It has to be healthy. It has to almost come in contact or come darn near those nutrients in order to take them up. When we look at those nutrients and what percentage each one of these mechanisms supplies, you're seeing nitrogen. Because it's mostly in the nitrate form in many aerobic soils, we're looking at mass flow, nitrate moving to that plant with that water. But when you start to look at other nutrients such as, and this is where my bifocals are killing me, diffusion, right? The movement due to concentration gradients, that's phosphorus, right? 94% of the phosphorus taken up by plants in this study was taken up by diffusion. The plant root almost had to come in contact with it. In fact, if you talk to many people, they're talking maybe 0.1 millimeters of movement a day. It's not going very far, right? Plant roots, important in this nutrient acquisition. And you all know this, right? I spent a lot of time in Shawano County. If you don't know where Shawano County is, it's northeast Wisconsin, up by Green Bay. It's cold, right? Every spring is cold and wet. Right? Spent 10 years in Missouri. I'm not used to cold and wet in the spring. And every year I go out and people are all upset, right? We see corn that looks like this. What is that? What's the deficiency symptom? Phosphorus, right? Purple means phosphorus. Every spring I go out and I see phosphorus deficiencies. They're like, I have a soil test. I have more than enough phosphorus. What's the problem? It's not because it's not there. It's because of acquisition. The plants can't get to it. Why? Cool, wet spring, stunted root growth, lack of diffusion, lack of water uptake in that cool, wet environment. Nutrients just aren't taken up. So when I talk about fertility, it's not just about supply, right? It's about, can the plants get to it? So they wanted me to talk about soil tests. All right, this is where I'm gonna have to really wave my arms and make this exciting, right? So this is where the chemistry begins. All right, I got him over there. He's excited about soil testing. They told me you were going to be a raucous crowd. All right, you're not letting me down. All right, soil testing, it's been around since the 40s, right? We know how to do this. It's not magic. It's science. But what I'm here today is to talk about that science, because sometimes when I'm out talking to farmers, we're misapplying it, or we don't understand it. It's maybe not a misapplication, it's that we just don't understand what's going on. When we think about soil testing, why we use routine soil testing is to gauge the potential amount of plant available nutrients in the soil, right? How much is out there? And that's the only way we can do it pretty much right now. We have plant nutrient testing, so tissue testing, but we also have soil testing, and there's been so much research in soil testing. This tends to be our go-to for gauging nutrient availability. So this testing is based on extensive, hundreds to thousands of field data or years crop growing data, right? To calibrate to this test to what we think a plant needs, right? So it identifies a non-responsive area, a responsive area, and predicts a nutrient application rate. I'm gonna go through all the science because there is a point in the end, don't worry, why I'm going through all of this. When you look at a soil, right, you send in that soil sample, what happens? They dry it, they grind it, and then they start to do extractions, right? They are using chemicals to identify how much of that nutrient can be extracted from a soil. They're trying to estimate how much of a plant nutrient might become available over the growing seasons. So it must be a correlation, right? So there's a lot of different extractants out there, but there must be a correlation between what is extracted and what a plant takes up. Each state's going to use a different extractant, and we'll get to that in a second. And these numbers don't really have, most of them don't have an absolute meaning. They're just an indice, right? When you think about how that works, right, you get very low, low, high, very high, right? They're indices when we think about fertility levels. Once we have that extractant identified, we then move into calibration. We take those soil tests and we go out for each crop, and we identify if we have a soil test level of this, that is this, low, medium, high, and this is the amount of fertilizer we need to apply. There's a lot that goes on there. You can imagine just in the state of Wisconsin. I'm told there's people from 10 states here, right? In the state of Wisconsin, you know, we have the Paleozoic Plateau, so karst areas down in the southeast. We have the glaciated regions in the north. I'm sand, Brown County, which is next door to me, is clay. Soil diversity is all over the board. It's a beautiful state when you want to look at soils. But when you want to make fertility recommendations, it gets really complex. And so all of these tests and these correlations, these calibrations are very intense, and they've been worked out over time, and they're based upon achieving a maximum yield. So I'm pulling this out of A2809. So if you're in Wisconsin, you know this. This is the fertility recommendations, and it was the first picture on my first slide. So coming back to the extension recommendations for nutrient or fertilizer applications, right? We're going to rank, after we extract that nutrient, we're going to rank it as, after our calibration, very low, low, medium, high, very high, or excessively high. It's based upon probability, and this is not what some people don't know, right? So what does a test of low mean? Well, it means that there's approximately greater than a 90% chance that you're going to see a response from adding fertilizer. It's not 100, but it's greater than 90%. There are certain conditions where it may not work. And this is where I love that we use probability, right? Because I see soils as individuals, and I hope you do too. Each one's going to act differently, even though they look very much the same. I explain this. I have a 7-year-old son at home, right? Maybe you have a 7-year-old son at home. They both get hives or prescribed Benadryl, right? Lucky you give your child Benadryl, and he falls fast asleep, and you get 2-3 hours of peace and quiet to yourself. I give my 7-year-old Benadryl, and it's a one-man Ringling Brothers circus. Why? They're both males, they're both humans, they're both 7 years old. What happened is that they're individuals. They have their own metabolism, they have their own biology. Things act a little bit differently because they're unique, and soils are the same way. And so when you look at the probabilities associated with, that's why it's not 100%. Each soil is an individual. Once we know that testing level, right, then all of this research identifies what the extractant level is to associate it with that level, that very low, low, high, very high. And then we calibrate that back down to how much fertilizer we need to apply. That's soil testing in a nutshell. Why do I point that out? This is where sometimes things go awry. And I just want to point this out. So you're still sitting there, Jaime, so what? Different states use different extractants. Different laboratories use different extractants. In the state of Wisconsin, for phosphorus, we use Bray 1. But as you look through there, you notice that there's also Malic 1, Malic 3, Morgan, modified Morgan, Olsen bicarbonate, H3A1. There are tons of different extractants out there that can be used. Different labs will use different ones. So if you're in the southeast, you might have a Malic 1 or 3. If you're in the northeast, you're looking at a Morgan or modified Morgan. If you're out west where the pHs are high, maybe it's an Olsen bicarbonate. Why that's important is going back and understanding the chemistry of soil testing is important, because if you send a test, for example, if you send a test to Missouri, and we'll get there in a second, understanding what you need for your state and your extension office will tell you what is a particular extractant. These are the ones that we require in Wisconsin. So if I go back and use my research discount at the University of Missouri, right, because it's a lot cheaper for me, they haven't figured out I moved out of the state 5 years ago, I still have that research discount. Is it gonna work? No. When you look at, and it's probably pretty small, when you look at the test procedures in the state of Missouri, the University of Missouri lab is excellent, excellent. I'm not bashing, they are fantastic. It's just that they use different extractants than I need in Wisconsin. They use different extractants than what the recommendations in A2809 are. They use a 1-to-1 salt water solution for pH. Wisconsin requires water. They use a Woodruff buffer for lime requirements. We use Sakura. They use Bray 1, we use Bray 1, but we also use Bray 1 for potassium, and they use ammonium acetate. You don't have to know what those words mean. All you have to know is that they're different. So if I send a soil test to a lab that doesn't use the extractants, they're in A2809, I can't use A2809 to make a fertilizer recommendation. If you send, for those of you in Wisconsin who have nutrient management plans, if you send them to non-certified labs, and Wisconsin, on the DATCAP website, these are the labs that are certified, then your soil tests aren't valid for a nutrient management plan. Okay. Those are just some nuances. All the labs out there that are certified are fantastic. I just want you to be good consumers of data. Okay. And know what you need for your state for your soil test recommendations, because they've been calibrated through all of those years of field research to that one particular extractant and analytical method.
Can I ask you a question?
Yes, ma'am, Erin.
I apologize if I'm jumping ahead.
No.
But organic is very based on biology.
Correct.
Organic, not big organic, quota organic inputs, but organic inputs. How does that relate to that range and that probability that you were talking about in terms of response and the fact that these are chemical extraction method, if we're really looking at biology in organic system, how can we, in organic, is there different ways we can use this as a guidepost or different, just your thoughts on
Yeah, in every system we use these as a guidepost, right? The whole idea of this extractant, and make sure I answer your question, Erin. The whole idea of this extractant is to gauge potential availability. So we're looking at many of the extractants contain an acid. What they're trying to do is look at that mineral weathering, right? They're trying to see what nutrients are going to be released from that soil. It doesn't do a good job of estimating what's going to come out from mineralization. And it doesn't matter whether you're an organic or a conventional system. This is estimating more of a chemical weathering process, not a mineralization process. And that's where this whole idea of soil health and soil health tests are coming about, and they're not perfected. And this is why I actually went here, Erin, is nobody really liked that talk right there, right? But it's really important, right? The important part is the calibration portion. The calibration portion, sorry, I wasn't dancing and waving my arms enough for him over here. It's all about the calibration portion, right? How many years did it take your state, our state, to calibrate, right? Years. We've been working on this since the 1940s. So do we have new extractants out there? Do we have new methods out there to try and gauge soil health and that mineralization? We do. They've come about within about the last decade. Have they been fully calibrated yet? No, not yet. Right? So I'm not bashing them, they're awesome. I'm really excited to see if we can use these tests to gauge mineralization, because we know we get a lot of nutrients from that organic matter. We know we get a lot of nutrients from that biological activity. We just haven't been smart enough to figure out how to estimate that yet. We're getting there, but it's going to take time. Just like it took time for our soil testing, the traditional quote-unquote soil testing, to evolve to a place where it's at now. And it's going to take that field calibration for your state, for my state, for your area, for my area, for your crop, for my crop. And it's a lot of work is still yet to be done. Does that answer your question, Erin?
No, that's working. That's great. That's exactly what I was asking about. There's a lot of interest within the organic community in soil health tests and soil biology, and as you mature on the organic spectrum of your biology, then changes nutrient availability. But I do want to stress these are guideposts, and this is still a way for you to look at the ebbs and flows of what's happening in the soil on your farm, even though they're, like you're saying, we're at the tip of the iceberg with some of these newer soil biology, soil health tests, and hopefully they continue to evolve. But this is still a strong tool to look at how your farm's progressing.
Right, and when we look at nutrient management in the state of Wisconsin, we have what's called adaptive nutrient management, right? So we know that these recommendations that we have may not fit your farm. And there's a whole program and process that you can work with researchers and you can work with your land con to tweak these recommendations for your farm and still meet nutrient management plan requirements and recommendations. Okay, so there's a lot of openness to this. Right? And so that's where, and I always want to point out, I love the, there's no one, I don't think there's anyone more passionate about soil health than myself, but I'm optimistic that we'll get there. I just don't think we're there yet. Yet. The key word, growth mindset, right? Yet on those. So the take home, good sample, right lab, right interpretation. And I don't care what nutrient source you're using. Right source, right rate, right time, right place. Right? The 4 R's of nutrient stewardship, both for crop productivity, economics, and environmental stewardship. So now I finally get to the part I really get excited about. All right, soil health, right? What is soil health? All right, we all know the definition. You've heard it a million trillion times. It's the continued capacity of the soil to function as a vital living ecosystem. Right? This is what's cool, and this is what actually gets to my heart as a person who enjoys soils as individuals. Each soil is a living ecosystem, and you know this, and we have to treat it as such. The whole idea is to allow the soil to be in of its own into perpetuity. And how do we allow that soil to function as it should function? So I'm a picture kind of person. So I'm standing in a soil pit in Shawano County, right? Shawano County over by Door County, out by Green Bay, if you're not from this area. Look at how beautiful that is. They laughed at me because I just sat in the bottom of the soil pit. You see that beautiful cover crop on the surface, but what you see is that dark color, for us that's really dark, cookie crumb structure, root growth. So what is soil health? I always have this picture when I talk about soil health. We look at it as good soil tilth. When you look at that soil right there, and you look at how you manage that soil tilth, right? I used to teach college. So imagine how, this is how I want soil to look. I want it to look like inflated basketballs in a box, right? Inflated basketballs in a box. Why? How well do those basketballs fit together? Not very well, right? It leaves a lot of pore space in there. That pore space for water and air movement and for root growth. Right, so we have that good soil tilth, we have that lack of compaction, we have those aggregates, we have that water and air movement that we need to make that a healthy and productive soil, not only for the plants, but those microorganisms that we're managing. We have to have sufficient depth, right? We don't want it to erode, we don't want a thin topsoil, we want a thick topsoil. There's something ingrained in us, right? I don't care where you're from. I'm originally from Iowa, but I don't care where you're originally from. Growing up as a child, you knew what was good dirt, right? At least those of us, my generation and older, probably those younger may not have ever gotten outside. But my generation and older, right? We know what good soil is. What is it? It's black, it's rich. Even as a 4-year-old, you could say, ooh, that soil's better than the other one because it was darker, right? And it was deep. We understood that there's something ingrained in us that understand what good soils are. So that sufficient tilth, that sufficient depth, good water storage. And these are all the definitions from the Cornell, from the Cornell Soil Health Test. Large populations of organisms, small populations of pests. Again, focusing on that biology. Sufficient, but not excess nutrients. That's why I'm in Northeast Wisconsin working on water quality. Green Bay, I don't know that we'll ever call it Blue Bay, but Green Bay is green at times because of excess nutrient load. low toxins, and resistant and resilient. And I know Klaus is going to be talking about resiliency later on in your keynote speaker, and I'm really excited to hear about that. Because talking about being able to withstand disturbances, whether it be drought, floods, so on or so forth. And I'll show you a soil that's not resilient in a second. How do we measure soil health? And Aaron was alluding to this. As a person who likes pedology, I separate them into the functional and the detailed approach. I'm a functional approach, right? When I walk out and I look at soil health, what do? I look at it. I touch it, I feel it, I use a penetrometer, I use a shovel, I get in there, I watch how water and air is moving, I look at the roots, I use my senses to gauge soil health, right? Because I want to know how it's going to function in that ecosystem. We can also look at a functional approach of measuring profitability versus yield, right? And we know that as we improve soil health, because of that increased microbial activity, because of that increased cycling, there's a potential that we may reduce the amount of inputs, whether that be fertilizer inputs, or pesticide inputs, as we try and control those pathogens, as we try and control those weeds and those insects. So how do we manage that in soil health? Cornell Soil Health Test. I like the Cornell Soil Health Test because I'm a functional approach kind of girl, and that's what it attempts to do, right? It's looking at fertility, it's looking at aggregation, it's looking at carbon sources, it's looking at how that soil functions within its ecosystem. So it's kind of a broad-based approach to soil health. You're going to hear from others today that look at more of these Tier 1 measures, and these are the 19 soil measures recommended by the Soil Health Institute for measuring soil health. Right? You notice they're very detailed. They're looking individual. Right? We can combine these together into an indice, but a very different approach. As Aaron alluded to and got me to talk about a little earlier than here, right? We're evolving. But this is what we're looking at. So how do we manage for soil health? And this is what Aaron was getting to. Organic matter, right? I cannot preach. So I can usually say I love two things. Soil aggregates and manure. Those are my two favorite things to talk about, right? Why? Because it has everything to do with this nutrient supply and acquisition. Soil organic matter, you've read that we estimate in 1% soil organic matter, we have 1,000 pounds of N, 100 pounds of P, 100 pounds of K, 100 pounds of sulfur for every 1% organic matter. If we can increase those organic matter percentages, we increase naturally, sustainably, and in tune with our biology, improve the fertility of our soil. Again, we talked about how many of you fertilized for X, Y, or Z. Many of you never raised your hands. Why? Because it naturally comes from the soil organic matter as it breaks down. To me, soil organic matter is the key, one of the keys to soil health, and is the key to organic management. This is where the fertility can come from. I'll let others talk about legume credits later on, and I'm just going to focus on organic matter. Realize it also has cation exchange capacity, but I'm going to focus on the nutrient status, right? Those of you, who are you from the Corn Belt, right? You betcha. This should look familiar. The beautiful drummer soil, nice wetland soil out of Illinois, right? You get happy when you see that, right? Look at that beautiful dark color. When we look at those beautiful prairie-derived soils with all of that organic matter. What was really interesting to me, when you look at the state of Iowa nitrogen recommendations, they tend to be a lot lower than the state of Missouri when I was there. Why? Because it was beautiful mollisol, organic matter. They fully expected a lot more nitrogen to come out of their soils. But don't be surprised. We can get that from even some of our soils up here in the north. So Larry Bundy, who used to be with UW-Madison, did a study looking at the contribution of soil nitrogen to yield. I don't care who I show this slide to, everybody's in awe. All right, this is contribution of soil nitrogen to yield, and I put a box around Wisconsin. All right, what does that number mean? According to Bundy's research, Wisconsin, we expect 71% of the nitrogen that are required to produce a corn crop in a continuous corn rotation to come from the soil. That nitrogen that we're adding just gets us the other 29%. Did you know that? On average, through the Midwest, we're looking at, in a continuous corn rotation, they estimated 56, about half of the nitrogen actually comes from the soil itself. It's that mineralization, it's that organic matter, it's those microbes that are out there helping to cycle those nutrients, right? I always tell the story when I used to teach college, right? The settlement of the West, right? At least in my mind, this is how it happened, right? Europeans came to the United States. We wanted to grow tobacco, so we cut down the trees. On the East Coast, we grew tobacco. And there's research to show that first year of tobacco, terrible, right? We switched it from a forest-derived system into an agronomic system. The microbes hadn't caught up yet, so first year of tobacco, horrible. Second year, third year of tobacco, stellar, right? Why? Microbes had picked up the pace. They broke down all of that native organic matter in the soil. Tobacco being a nutrient hogging crop. Great tobacco. Years 4, 5, and 6, yields declined, turned to zero. What happened? We moved west, young man. Cut down more trees, right? We have always relied on the soil to provide our nutrients. In that system, they didn't, that I just described. They didn't have fertilization. They had to move on. They didn't have the techniques we have, but we have techniques to maintain this organic matter percentage. So I'm going to ask this question because you're tired of listening to me already. What is your soil organic matter level? Shout out a number.
3.5.
3.5. Excellent.
Less than 1.
Less than 1. I see a lot of those too. Don't be shy, right?
2 to 3.
2 to 3.
4.
4. I love it. We wanted to put this in perspective. And so, again, realize I'm from Northeast Wisconsin. I live in Shawano. It's sandy. My organic matter percentages are in the 1 to 2 range in agricultural systems. But what were they natively? We wanted to figure that out. So the NRCS and I worked together along with Francisco Arriaga here on Madison, and we measured baseline soil organic matter levels in what we considered mature, non-disturbed forests, because we would have naturally been a forest-derived soil. What were those organic matter percentages for me in Northeast Wisconsin? When you look at the literature, forest-derived systems should not have organic matter, right? They're not the prairie-derived soils of the Corn Belt. But what did we find? I'm going to use the words OMG, right? This is what our natural soils would have had for soil organic matter levels, we estimate. 8, 10, 9. And in my sandy soils of Shawano, where we now have 1 to 2%, originally would have had around 5 to 6. When we think about that 1% organic matter I have right now, back to a regular 6 that it should have had, that's 5% organic matter. That's 5,000 pounds of nitrogen, 500 pounds of phosphorus, 500 pounds of potassium, 500 pounds of sulfur, all of those micronutrients, all of that CEC, all of that carbon source for those microorganisms, all that water holding capacity, all that glue for aggregation, and it goes on and on and on and on, right? What have we done? We have destroyed it, right? Can we bring it back? And that's where providing long-term solutions. Yes, we can, but here's where you need to be realistic. So when we look at organic matter accumulations, I'm going to compare and contrast. It all depends upon where you're starting from and your biological system. Your sleeping child versus my Benadryl hyped up crack cocaine child, right? Biological systems, very, very different. So Francisco and I would have worked down in Manawa, which is Wapaka County, which is across from Stevens Point, right? Which is, for the rest of you, center part of the state-ish. Right? Rocky, sandy soils. What we did is introduce 3 years of cover crops, not a research study, a demonstration. We took 3 years and introduced a cover crop every year in this really poor, horrible, terrible, I can't use enough negative terms to describe this soil, right? Something that really could use improvement. We went in 3 years from about 1.2% organic matter to 1.6. Okay? Francisco estimates in 1.7 years, we will reach 2% organic matter. We will have almost doubled. In 6.6 years, if we follow this huge if, we follow the same trend line, we may bring it up to 3. But we also need to be realistic. Compare that to when we look at the practical farmers of Iowa. They have a 7-year study of rye coming into a corn-soybean rotation, or continuous corn rotation, excuse me. They saw no change in organic matter percentage over time. So we have to be realistic. Is that soil better off under that rye? Yes. We just haven't measured it. And that's why I personally don't like to go back with those 1 point pinpoint kind of measurements, right? Because it gets you discouraged, right? It's not looking at the function of the soil. Yes, sir?
With that test, what's the maturity of the rye that killed it?
That is a great question. I will send you to this website, right? Not my research, right? It is about, pardon me, yes, sir. The question was, what was the maturity of the rye when it was terminated? That would be an excellent question, right? And why are you asking that question? So you're tired of hearing me? I'm going to make him talk.
Why am I asking it?
Yeah, why are you asking that question?
Because the more mature it is, the greater the chances are of building organic matter.
The more mature, his answer was, the more mature it is, the greater chance of building organic matter. Why? More roots, I like it.
Carbon and nitrogen ratio.
Higher carbon to nitrogen ratio. What does that have to do? So he said higher carbon to nitrogen ratio. I'm guessing Aaron and Matt are going to get into this. Yes, no?
I think Matt gets into it. I don't know if I'll get into it.
All right. So what in the world did we just go into? We went into chemistry again. Carbon to nitrogen ratio. What is that? Right? And what are they even talking about? And this is why this is so hard. And I love the question. I do. I'm not picking on you. I love the question. This gets to the complexity of trying to measure changes in soil health, right? Because it depends. What was the maturity of the rye? The greater maturity of that rye, the more salacious, the more lignaceous it is, right? Excuse me, the more lignaceous it is, right? The higher the seed-end ratio. What did I just say? The harder it is to break down. It's not soft and tender. Microbes just can't eat it up like Skittles. They have to work on it a little harder. And that leads to increased organic matter contents. Is that where you're going, sir?
Yeah.
I can't read you're too far away. You're safe. I can only read the front row. All right?
But when you give a presentation, it would be really good if I knew what the maturity of that rye was, because this research means nothing to me when I have no idea what the maturity was when they terminated. It means nothing.
I love it. And that's where I am giving the general talk this morning, right? That's where I can, am I passing the buck? Yeah. Yes, I am. Right? I am your introductory soils professor for the morning. So, you know what? You got some really smart people coming up, and you are going to hammer Matt Ruark on that. Is Matt here? No, he is not. You are going to hammer Matt Ruark on that, because he is making a very important, very valid point, right? It all depends. I agree with you 100%, sir. That's where I love when these get feisty, right? It is. And the reason I point that out is that is why I have to stand up here and wave my arms. We are not there yet. It all depends. 3-brain circus, sleeping child, right? Why? What was the maturity of that cover crop, right? It has everything to do with that. That is a detail they didn't give me time to get into this morning. They gave me an hour and 15 minutes, right? To cover soil testing, soil health, fertilizer management, introductions, just random crap that I will talk about to keep you entertained. They gave me 75 minutes to do that, all right? So I have to be fairly general, but you are right on. And that's what I love. When you look at this information, being good, thoughtful consumers of information, critical thinkers is very, very important, right? Because a lot of us will stand up here like I'm doing right now and wave my arms and talk generalities. But in all reality, it's about the details, right? Would you agree with me on that one? It's on the details. Yes, sir.
I'd throw out another question. What is the quality and the nature of the organic matter? Because not all organic matter is the same, and we treat it like it's just one number.
I love that. I was waiting for you all to yell at me about how did you measure organic matter? Was it dry combustion? Was it total organic matter? Was it POX? Was it particulate organic matter? You know, what kind of extractant did you use? How did you measure it? When did you measure it? So on and so forth. I was waiting for that question, right? It matters. It really does. And when you look at these measurements, these are dry combustion soil organic matter, right? This is that total organic matter fraction within the soil. Will we see short-term changes in soil organic matter if we're measuring total? Probably not. Maybe not. And that's why when you talk to these scientists and we go back to the measurements, they're looking at specific fractions of organic matter. They're very sensitive to changes in management. They're very sensitive to microbial activity. You agree with me?
I've got a data set.
Awesome.
In 6 weeks, it went up 1% across a really wide, statistically significant sample.
Excellent. Will that happen everywhere? No.
Won't happen again in that spot.
That's where all of this is very, very specific. And so let me get ahead on going here. What do I love about increasing organic matter? And this gets back to who is out there doing the cycling. And this is where you talk to your microbiologists. So just doing a visualization study, I work with a lot of farmers. They don't believe me oftentimes that there's critters out there, right? You can't see them. Are they really there? Right? So I couldn't do the NRCS underwear study because they didn't want me to bury underwear with farmers, so I had to use cotton cloths, right? So we buried a white cotton cloth in the soil at 2-inch depth on this, and around June 20th, excavated it back in July 20th, buried it 2 inches in depth, laying flat in various rotations at a 2-inch depth. What happened to it? Again, visualization, not research. Looking at the importance, and the whole point of this study was to drive home the importance that there are different microbial communities out there doing this cycling for us. When you look at that mature woodland soil, you notice that the cloth looks almost exactly the same as it went in the ground. Why? Somebody answer me why.
Nowhere to eat it.
Huh?
Nothing to eat it.
Nothing to eat it. Actually, there was. They're just so darn slow at doing it, right?
Fungal community.
It's a fungal community. And so this is when you look into the literature, when we look at microbial communities and forest-derived systems, much of the research will tell us that it's a fungal-dominated community. It's going to cycle nutrients slowly. Why? Because those trees, even though we have this, we imagine that they need a lot of nutrients to produce that leaf matter, they don't. Right? They have evolved over time to cycle nutrients slowly to meet the needs of that ecosystem and to reduce the amount of loss. It's a fungal-derived ecosystem. When you look at those bacterial ecosystems, you'll notice the corn soybean rotation tillage with manure. You notice 4 weeks later, bam, gone, right? I don't have the data back. We're going to make an assumption, right? What kind of community is active there? Bacterial. Again, when we look at these systems, the complexity, and that's, as a pedologist, that's why I get so excited, the complexity and data interpretation, right? Who is there? What kind of, and what quality of matter is going in there? It becomes very important. Let's just look at pictures, right? Because I have a few minutes and I just like to look at pictures. When you look at that supply of nutrient into that system, right? Do these look good? Is this soil healthy? What do you see on the left-hand side? You see a hole. Excellent. I love Mr. Obvious. All right. Thank you. So yes, it is a hole in the ground. I like to call it a soil pit, but you can call it a hole if you'd like. What is it? What do you see? This is in Omro. This is down by Appleton. This is central Wisconsin.
Several hard layers and a hard subsoil.
Yeah, it looks pretty crappy, doesn't it? My eye was always drawn to that dark layer in the middle. What is that?
Accumulation of organic matter.
True, it is an accumulation of organic matter.
Silt deposits.
Silt deposit. Why is it in the middle of the soil profile?
Water carried it there.
Nope.
No.
These are not spodosols.
Oh.
So good call. I love this. Soil scientist went to a smodosol. He was going to a podzolization, right? So no.
Haven't tilled deep enough to get there?
Haven't tilled deep enough to get there. Would you believe this is at the bottom of a landscape, bottom of a hill slope? That was the soil surface. That is a beautiful silt loam, organic rich silt loam, that now has about 2 foot of stuff, gross stuff, heavy red clay on top of it. How well can that soil provide and supply nutrient, right? It's man-made impact. That is one way. Erosion is one way, right? We reduce the amount of supply. What about the picture on the right? That's Missouri. So we'll take you on a quick tour. Let's see, tour. I picked up a southern accent when I said Missouri. What is it? What do you see there?
Aggregates.
Aggregates. He sees the high smectitic clay content of the soil and all of that cracking. Right. It's not what I'm looking for.
You got roots down there.
I do have roots down there. Why is the surface, do you notice the surface is lighter than down below? Why? And it looks like one big gigantic clod.
Until.
That's tillage, right? Why tillage? When we look at introducing, so these ecosystems, this soil has developed over time, right? To have a limited amount of oxygen in it, right? Diffusion of oxygen into the system is fairly slow, right? And the ecosystem developed that way. When we disturb that ecosystem, as we introduce oxygen into the system, right, we get a flourish. If there's organic matter, we get a flourish in microbial activity and decomposition. We burn, the term burn off that organic matter. When we burn off, yes, sir.
You say we want biological activity, so there's a contradiction there.
There is, but why?
Good question, Jaime.
So he said, we want biological activity, but we just till the soil and we increase biological activity, and now I said that's bad. That seems like a contradiction. It does. So why? Damn you, Jaime. You just said you've alluded that we want more activity, and now you just said we don't. What? You are just the worst presenter ever. You make no sense. I love it. Why? Yes, sir.
The activity is like taking money out of the bank. We're burning up organic matter to release minerals to make the next crop grow. The question is, are we putting as much back as we're taking out?
Exactly. So it's all about a balance. So he said it's to summarize, he talked about mass balance, right? What comes in has to be at least equal or greater to what goes out. Right? When we till the soil, oftentimes that oxygen stimulates more going out than what's coming in, right? And we see that organic matter decline over time. When you raised your hand and said, I have 1%, I have 3%, I have 4%, and I showed you a slide that showed, at least in northeast Wisconsin, we're looking at 6 to 10%. Where did it go? Part of it was erosion, you saw that. Part of it is decomposition. As we stimulated that system, can I use that word? Overstimulated that system by introducing oxygen. So tillage is oftentimes a very important part of our pest management scheme, right? I am not anti-tillage. I am proper tillage when it is needed, right? Reductions where we can. Because you can imagine all of these organisms, right? Again, a visual person, when I see this soil and when I see that porosity, I see these little guys hanging out in their homes, right? Those organisms are living in that pore space, in that they don't live in the walls, they live in the interior of their home. And whenever we move through that soil with a tillage implement, we destroy their home, right? You rip the roof off, you destroy their walls. And when we do that, they try their best to survive. They break down that organic matter, they try and recover, but ultimately you end up in a decline because they just can't survive. Yes, sir?
When you put nitrogen fertilizer down, you're setting the soil on fire too.
Yes, when you depend on the form of nitrogen fertilizer. I like to talk about anhydrous, right? I use anhydrous all the time in Missouri, right? It was a cheap, readily available form of nitrogen. We also know it's an excellent, I remember, and I can tell you from my graduate days in Oklahoma, I can tell you it's an excellent soil sterilant. So yeah, graduate students, sorry, sometimes just screw up royally. And we over-applied anhydrous. When I mean over-applied, I mean by hundreds of pounds. Ruined that soil, made for a great microbiological study because nothing came back for years after we sterilized it, right? Because that ammonia converts over to ammonium, but then it converts over to nitrate and you get a complete acidification of that soil. So all of this is a delicate balance. Y'all staring at me going, wow.
Well, in organic, it's not, anhydrous obviously is not organic, but there are organic fertilizers that do have that really revved up
You betcha.
activity. So I really love Klaus's comment that it's all about understanding this and knowing how to balance, put deposits back in the bank, cover cropping versus smart tillage. I do a lot of organic no-till, but smart tillage I think can still be a strong tool for us. So just understanding this biology and ecology
So what do you consider the hot nitrogen fertilizers?
I'll pass it to Klaus as well, but I think Chilean nitrate is a pretty hot source.
It's the hottest one. It's actually the hottest one.
Hottest one, Chilean nitrate. So composted products add the biology. So that's where again you're looking at sometimes manures. They can be really readily available, but you're putting currency back because you're building the communities. But whether or not the pelletized poultry manure that has been heat treated versus composted, I would argue that's a pretty hot source. So there are some hot sources, not in hydrous, but still we need to think about that concept of how versus cover crops and organic matter base.
Well, that's
Pit manure on a slurry is very, very hot.
and the reason I brought up anhydrous is in my little chemistry brain, they're all, anhydrous is just the component of an ammonium-based fertilizer, right? So for those of you like, Jaime, that doesn't have anything to do with us. Sorry, it's my chemistry background, NH3, ammonia. And many of these sources we're talking about is NH4, right? So you apply NH3 to the soil, it's going to consume a hydrogen, it's going to bind that, and you end up with ammonia, the same form that we're using in many organic sources and many of the manures that we're using in many of the basically meals that we're using. So chemistry's chemistry, right? I just went all the way to anhydrous, but in all reality, I was just missing a hydrogen, right? Is all I was doing, right? There are some hot sources. Poultry manure, I know I can burn the crap out of stuff with that because I'm not very good at applying it, right? Fresh, don't do that, right? Very, very high in ammonium, right? Lots of things can happen. So it's all about managing that nutrient supply. I am a huge proponent of soil organic matter. I'm a huge proponent of maintaining that biological activity, also for nutrient acquisition. So when we talk about that supply, again, I apologize, I'm just providing you the basics so that Klaus and so that the rest can really drive home and get in depth with this. But when we think about nutrient acquisition, this is where I get really passionate, right? So not the chemistry, but rather the physics of that soil. Making sure that we have that aggregates, we have that pore space, we have that lack of compaction in that soil, because just because the nutrients there, I spent all that time, that money, that effort to put that fertilizer source, that organic source in the soil, but if the plant can't get to it, it's all for naught. Because I go out and I see this. I can tell you that most of the time I don't stand in rooms waving my arms in front of people at tables. I run through soil pits waving my arms with a knife. All right, that's where I'm more comfortable. All right, I'm usually knife wielding. All right, it's scary, huh? All right. But this is what I see. I don't care where I go. If I go from an organic vegetable field, if I go to a conventional field, if I go to a pasture, the one thing that I've learned as I move across the state of Wisconsin is that I see this, right? Okay, I'm ready for Captain Obvious. What do you see?
Sideways.
Roots growing sideways, perfect, right? You see that big old plow pan right there in the center. And those roots, when I pick them out, they weren't going down. It looks like they're going down, they're going sideways. Right? When we think about nutrient acquisition, we talked about how plants take those nutrients. It may be mass flow, it may be diffusion, it may be root interception. But if we can't get a root system any further than 4 inches into the ground, where we can't tap those nutrients, tap that water, down below, it's all for naught. This is where, when I talk about smart tillage, right? How do we fix this? I always get this question. How do you fix that?
Cover crops.
Slowly over time, right? I would advocate cover crops. Definitely is going to be part of the system, right? Gypsum. So if you have a sodium issue, so what gypsum does is, so it will potentially, if you have a dispersing of those clays, right? That calcium can help bring those clays together.
You need some tillage until you can straighten it out.
That's my man. We're going with some tillage, right? So this is one of the areas where I do advocate for tillage, right? Research has shown if we don't break up this plow pan, it's going to reduce yields perpetually. Studies by Penn State have shown that at this depth and below, oftentimes at the end of their 12-year study, that compaction persisted even after natural measures, right? So what am I advocating? Deep, if it's there, and this is where you're gonna call me and we're going to go out with a penetrometer and a shovel, or your NRCS personnel or your LandCon personnel, and identify this is really what your issue is, and then deep ripping, and then coming back with cover crops. Fracture that up, and then keep those fractures open with a root, right? Because when we look at these, and you all know this, I don't care which farmer I'm talking about too, right? We know the headlands are less productive for many reasons, but we know those headlands tend to be less productive because of compaction. Research has shown 20 to 50% reduction in yield where we have compaction. When we start putting dollar signs to that, it gets quite tremendous. And like I said, it doesn't matter where I go. Sorry, Roger moved away from the screen. I don't matter where I go. What do you see here? This is Marinette County, so I'm almost, so for those of you not from Wisconsin, closer to Canada. What do you see?
Shallow bedrock.
I love that answer. There's no bedrock in that picture. But you drove home my point. Thank you, right? That, huh?
That's a fragipan?
That's not a fragipan. We don't have those in this area.
Yeah.
That's just a subsoil.
Okay.
That is a heavily compacted subsoil. What I want to point out in that picture is, look very closely to the left, right? You see those roots? There are a few roots getting down there, but they're only going through former root channels, right? Primarily. I walked out on this field. It was dry before that. They had received a 1/4 inch of rain the night before, and this was an absolute soupy mess. A 1/4 inch of rain should not do that if the soil was functioning. Should have soaked right in. But because that compaction was there, I'm not getting access to those roots.
Now, if you put a penetrometer in there, did it get softer again after you got?
Yeah, if I could break through, do I have a laser? I have a laser. So yeah, after you got through, you can see the roots are kind of stopping right here. If I can get through this layer where you start to pick up that grain, it would get softer. So that's where, invite me out, you'll have a good time. Because what happens when I punch a penetrometer through there? I end up with my face flat in the dirt, right? Once you punch through it, because you're trying so hard, you're laughing because you've done that, all right? You're pushing so hard, you just face plant, all right? When you break through. Doesn't matter. There's vegetable production in Green Lake County. This was a great pit, right? Because I could walk up, you can see the end. There's beautiful organic matter. Supply isn't the issue, it's acquisition. Look at how compact that surface layer is. I could actually go in there and take my hands and lift up that soil surface and carry it around. So it's more than just, when I talk soil health, again, when I look, and fertility, it's more than just having the nutrients out there. To me, and my passion, it's about allowing those roots to get there. And we're doing a poor job in certain situations of allowing the roots to get there. You'll notice this, I pulled this out, roots are growing sideways, flattened against that ped, right, out of that plow layer. So what's the problem with a little compaction, right? So we talked about nutrient acquisition, but when I talk about soil health, this was a graph, so those of you here, Shawano, I can't see from here, I think it's in this area right around here. We received 7 inches of rainfall in one day. What happens in Shawano County when you receive 7 inches of rainfall in one day? This. That's one rainfall event, ladies and gentlemen. So when we talk about nutrient acquisition, and we talk about soil health, and we talk about compaction, and we talk about managing our soils, I always throw this in here because to me this is a wake-up call. When we talk about, and you're going to talk about resiliency, right?
Or whatever anyone wants to hear.
Or whatever, and as you can see, whatever anybody wants to hear, I highly recommend doing this. This gentleman over here likes that, all right? So that is what we're talking about when we talk about resiliency, right? Can we fix that? Not for the long term. It's going to take a while. It also talks about microbial activity. And when we think about acquisition, and this is where later on I'm sure your speakers are going to talk more about the biological component and the wonders of mycorrhiza. Again, I'm providing the generals, right? Who knows what mycorrhiza is? Back of the room, yell out something. Ooh, the two gentlemen in the back. What is mycorrhiza?
Fungi.
You betcha. Good or bad?
Good.
Excellent. What do they do?
Convert the interface between the roots and the bacteria.
Excellent. So I'm sure, the reason I asked this is I'm sure there's a microbiologist in here that wants to answer this question for me correctly, right? Is that you, sir?
I'm sorry.
Was that you, sir? The really smart microbiologist that wants to answer this question for me?
Yeah.
Okay, just checking. You had me fooled, all right? So this is a beneficial fungi. We know that it produces organoproteins. We know that it is responsible for gluing those aggregates together. We know it provides that interface, right? It infects those roots. For me, when I think about how it expands that root system, I'll come back to that slide again. To me, it's about expanding. When we talk about fertility, it's about expanding that root system, right? So I stole these pictures. The slide is at the source is at the bottom. But the whole idea is our plant roots can only go so far, right? We're talking about plants taking up nutrients through diffusion, moving short distances, through root interception, right? We have to have those roots out there in order to get that uptake. This fungus assists us, and you can see those beautiful little mycelia, right? So when we think about those soil beds, right, we see them, we see the large pore space in between, but in all reality, inside those pores are tiny little pore spaces, right, that we can barely see with our eye. And inside those tiny pore spaces are the water and the nutrients that we need, and these little microfilaments can get in there. They're helping to bind that aggregate together, and they're helping to take up that nutrient. In fact, when you go into the literature, can I put a number to it? Again, it's a generalized number, but when we look at this number, mycorrhiza can, in one study, showed that it could increase soil exploration by 700%. 700% greater opportunity for that root and its friend, the mycorrhizal fungi, to come in contact with the nutrient that we need to take up. We know that other studies show that mycorrhiza can contribute to up to 80%. We know 80% of that phosphorus uptake. So it's not the roots necessarily that are taking up these nutrients, it's its friend, the mycorrhiza. Up to 10% of potassium, 25% of zinc, so on and so forth. So when we talk about soil health, this is a whole realm that we don't necessarily pay attention to, but we need to foster these organisms. I work a lot with the tribes in my area, and they always just say, Jaime, you're just so far behind, right? We knew this centuries ago. And I'm like, okay, explain to me. We knew this centuries ago. When we went and we opened up our garden beds, we always left the elder plants along the outside of the garden, right? Those elder plants such as sunflower and compass plant and nettle, those elder plants taught our garden plants how to grow. They helped our garden plants grow. They ensured that we had a food source to get through the winter. What were those elder plants doing? They probably served as an inoculant, a host for these fungi. We now know, and this is where if you go into the literature, it's really fun, right? I love to think about the soil as a being, right? With a voice and a life of its own. If you go into the literature, we now know that those mycorrhiza act as a superhighway. Those mycorrhiza, one plant says, hey, I need a little phosphorus. A plant says, hey, I got you some. Sends it through the highway system. We know that this mycorrhiza hyphal network connects in low testing soils, will connect that legume plant with that grass and will facilitate the movement of that nitrogen from one plant to another. That's amazing, right? That's incredible. How do we foster that environment? And this is where Aaron and Matt will be talking later on. When we think about keeping these mycorrhiza in the soil, we have to keep them there by giving them a home and a food source, right? That's where cover crops come into play. Not the brassicas per se, but where cover crops come into play. Yes, ma'am?
So in conventional systems, they're putting fungicides in furrow. Would those fungicides affect mycorrhizae, or is that different?
Yes. So
Good question, Jamie.
So the question was, so in conventional systems, oftentimes they put fungicides in the furrow. Does that have an impact on mycorrhizae? The research that I've read says yes. So it may not completely eliminate that mycorrhizal population, but it will set it back. And so when we looked at, and I was worried about this when I was living in Missouri and soybean rust came through, the threat of soybean rust, Asian soybean rust, because when we looked at how we would control Asian soybean rust in conventional systems, is I was going to have to use a fungicide at high pressures, bounce it off the soil to coat the underneath of that soybean leaf. I was basically going to blast fungicide into the soil and hope some bounced up to provide a protection against that Asian soybean rust. The answer is yes. To what extent and to what populations? Still to be determined, but the answer is definitely yes from the literature that I've read. Anybody else want to answer, provide insight?
I also will say that potentially our modern crop varieties, because there's a cost. I mean, it's not a completely generous relationship. The mycorrhizal fungi are beneficial to the plant, but the plant feeds them sugar. So if the plant is fed a high and readily available diet, they're going to shut off the mycorrhizae. And some of that breeding in a conventional system may have bred the intensity of the crop to associate with mycorrhizal fungi. So there's, I think it's really a huge, in terms of resilience and optimizing crop nutrients, the more we understand about how we've impacted these systems, the more we can better, through breeding and crop variety selection and management, look at fostering these incredibly valuable, and aggregation, I mean, the nutrient aspect, but the fact that these, like you put this on the slide, Jamie, glue together soil aggregates, which is such a key point of soil health, another huge role of these fungal communities.
Most definitely, and that's what when you look at providing an overview of this whole microbiome population, I find it just absolutely fascinating. And my numbers may be off, but the literature that I read told me that 40 to 60% of the photosynthesates in that plant are actually exuded through the roots. Yep. So 40 to 60% of the sugar produced by that plant is leaked out of the root system to feed these microorganisms. Right. That's incredible. An environmental system doesn't do that unless there's a payoff. Right? We don't spend all of that time, me and the other plants, just don't spend all of that time photosynthesizing to make sugar to give it away if there's not a benefit for me. And that benefit is feeding these mycorrhiza. And that's why I have at the bottom, roots are not passive players. We could spend days talking about the rhizosphere chemistry and what actually happens with those microorganisms next to that root system, and the chemistry and the biology and the biochemistry that's involved as we exude organic acids, and those organic acids release those nutrients, and so on and so forth, and that interplay with those microorganisms, right? We could spend days talking about that.
You have 3 more minutes, Jamie.
But we're not, because we have 3 more minutes. Don't worry, Erin. So I was going to end on this slide, right? That's why I went here, because luckily there's a clock right there, and I know the hook is coming. So, all right, this is when I get into a soil pit, when I'm a knife-wielding maniac in the bottom of a soil pit, this is what I love to see, right? This is a healthy soil. This is aggregation. This is biological activity. I see those mycorrhiza. I see those roots. I see those earthworm channels. And with that, I know I'm going to have better nutrient acquisition than if they weren't there. Yes, sir.
Got to the point that I want to ask a question about. Much earlier slide, you talked about the available nitrogen from the different states that was available from the soils. Was that conventional soils, or was that soils that were soil healthy?
Those would be conventional soils, right? So when we think about, and that's where I actually did literature, when did we start thinking about soil health? I had to actually go back. I knew it was new to me, right? So I went to college in the 90s. We called residue trash. It was better living through chemistry. It's actually in the 1990s. And so when we look at where much of this research has been done, in the time period in which much of this research was done, there wasn't as focused on soil health at that point in time than there was now. And so that's where all of these wonderful researchers like Erin and her crew are working to update that information and to provide us better information, because it is that how better living through biology rather than better living through chemistry. And we're getting there. But there's a whole lot more to learn, and it's the devil's in the details, as this gentleman is still smirking at me, right? Devil's in the details.
I love that, too. Better living through biology with organics.